All right, let's see. So while this is loading, I want to tell you how I'm going to do the lecture. Just real quick, attendance is up to date. All the outstanding homework's been graded. I'm still working on exam 2. I'm going to give you a homework assignment today, due Friday. Okay. Now the way this is going to work is I'm going to talk a little bit about how MASTAN operates, and then I'm going to give you a sort of a tutorial that'll go through building a model. You're more than welcome to work at your own pace if you want, but I want to explain a little bit about what MASTAN is doing and why it's doing it and how it works, because most structural analysis packages work exactly the same way. They all kind of use the same procedure. Let me talk to you a little bit about MASTAN, and I said this before lecture, and I think that barring some Windows version issues and whatnot that we're experiencing this morning, and maybe some Mac version issues, the program does work on both Windows and Mac, because we've got Windows and Mac computers in here that are running it right now. So, but to give you a little bit of background on it, it's very easy to learn. It's very powerful. It's 100% free. I have to give a shout out to Professor Zimian at Bucknell, who's made it free for everybody, which is great. It can do a wide array of different types of structural analysis. It can do linear stuff, nonlinear stuff. It can do buckling. It can do vibration. It can do 3D problems. But for us, we're focusing on linear elastic analysis in 2D. That's what we've been doing this whole semester. But I just want you to know that it can handle a lot more. One of the things about MASTAN, and this is true of all other structural analysis packages, is that it makes no distinction between a structure that is statically determinate and one that's indeterminate. It handles them both the same way. And so I kind of want to talk a little bit about indeterminate analysis today, so that you have an understanding of what the challenges are, how would you approach it, and how MASTAN does it. This program can also be used for like steel design and concrete design, because whenever you take those courses, you have to have some basic skills in structural analysis in order to design the elements. That's something I wanted to mention. There are some limitations that you do need to be aware of. It cannot handle triangular loads or trapezoidal loads or anything like that, and it can't handle moving loads. We're going to talk a little bit more about that later this week. But if you're feeling pretty adventurous, the source code is available. For those of you that are having challenges with installation, I would suggest that you try and install MATLAB like right now. And the version 2 on the website is the standalone. Version 1 is the MATLAB source code, and you should be able to just run the source code from MATLAB, and it's the same thing. So for those of you, as we start going through the exercises, I might help you out with that. Okay, let's have some just discussion about indeterminate structures, about how we approach them. And again, you feel free to continue to try and work on your installations and whatnot, but I want to give you a little bit of background about indeterminate structures. First off, why would we use them, and what are the challenges in analysis? So why use an indeterminate structure? Why even bother? Well, there's 2 real good reasons. The first is that you actually reduce your structural response. So if I have a beam that's simply supported and I have a uniformly distributed load on it, symbolically, the deflection is 5WL to the 4th over 384 EI. Now this is a determinate structure. If I take the ends and fix them, it becomes indeterminate, but the deflection gets reduced by a factor of 5. Instead of 5WL to the 4th over 384 EI, it's now just WL to the 4th over 384 EI. So to put some numbers on it, if this beam deflects 1 inch, this only deflects 0.2 inches, okay? So, I mean, just by making it indeterminate. Same thing with the moments. You know, we have WL squared over 8 here at midspan. Here we have WL squared over 24, and then WL squared over 12 here. So we reduce the moments and the deflections by making the structure indeterminate. We also add a degree of redundancy whenever we add indeterminacy. So if I have a 2-span bridge and I put a hinge in the middle, that makes it determinate. That makes it us able to do the analysis. But if somebody knocks that pier out, that bridge is unstable and it's going in the river. Whereas if the beam is continuous across the pier, that's an indeterminate structure. But if the pier gets knocked out, theoretically, the structure is still stable. Now, granted, you'd have to design the beam to be able to handle those additional moments, but the structure is statically stable. and can handle that, that failure of that main load-carrying component. So there's a reason to use indeterminate structures, but the problem is the analysis. So let's consider this beam. I just made this beam up. It's statically indeterminate to the first degree, okay? How many reactions do we have on this beam? 2 here, 1, 1, right? No internal hinges. So R is 4, E sub C is 0, R minus EC plus 3 is 1. So we have a structure that is statically indeterminate to the first degree. There are 4 reactions, but we only have 3 equations of equilibrium. So we have one more that one more unknown. We need another equation. Okay. Now, the reason why we haven't directly talked about indeterminacy until now is because you cannot analyze an indeterminate structure until you understand the relationship between forces and deflections. Okay. I propose that in order to analyze a statically indeterminate structure, you need more than the equations of equilibrium. So here's the 4th equation that we could use. So we have sum of forces in the x direction is 0, sum of forces in the y direction is 0, sum of moments is 0. Here's your 4th equation. What's the deflection right here? 0. There's your 4th equation of equilibrium. Or it's not an equation of equilibrium, it's an equation of compatibility. The fact that the deflection at B is 0. So what we could do, if we wanted to solve this problem, this is an approach. In fact, whenever you're going through and doing the math, this is the first approach that you use to analyze a statically indeterminate structure. What we'll do is we will remove support B from the structure. Take it out and allow the beam to deform. Okay? You got it? Okay. Did that work?
Yeah, I just updated my laptop.
Okay. You might want to try to do a Windows update on yours and try it again. I also have a sort of a fresh install file on this, so we'll give it a shot. Okay. All right. So we could remove the roller support at B and allow it to deform. So let's say we allow it to deform, so it deflects. What you could do is compute that deflection, okay? So I did that for you on this beam, and so it deflects 4.22 inches down, okay? So that's if the roller at B is gone. And then the question is, okay, if it deflects downward 4.22, well, how much upward load do I have to put up at point B so that it pushes it up 4.22 inches? Does that make sense? And whatever that upward force is, that's the reaction at B because it results in net zero displacement. Does that concept kind of make sense? Okay. So if you do the math, you get the reaction at B is like 63.75 kips. And once you have the reaction at B, then you can use equations of equilibrium, sum of forces and sum of moments to solve for the rest. You get your reaction at A and your reaction at C, and then you can draw shear diagrams, moment diagrams, etc. That is a method. We have a name for that method. We call it the method of consistent deformations, okay? Because the idea is that when you sum those displacements up, the displaced shapes superimposed together represent what's really going on the final structure. Does that make sense? Okay. Now, that's fine and dandy if you're doing a simple problem with maybe 1 degree of indeterminacy. And I would argue it is probably the most efficient way of doing it by hand, again, if you have a small degree of indeterminacy. The problem with this approach is that we have to choose the redundant, okay? So in that problem, I said, what's the deflection here, okay? But what if I said, let's not use the deflection at B. Let's use the deflection at C. That would completely change how we do the problem. Now, to be clear, the structure doesn't care how we do the problem. The answers are the answers, right? But if we changed our redundant choice, it would completely change our process, okay? And the problem is that makes the method difficult to standardize, and particularly it makes it difficult to write a computer program to analyze it, okay? That approach, this method of consistent deformations, is what's called a flexibility method. There are 2 classes of methods that we see in indeterminate structural analysis. One of them is a flexibility method, which is the goal is to solve for an unknown reaction or an unknown force. The flip side to that is what's called a stiffness method. And in stiffness methods, the primary unknowns are the deformations, the displacements. And that is much more easy to standardize when you're writing a program. Matrix stiffness analysis is how virtually every single structural analysis software package operates. I don't care if it's MASTAN, RISA, Bentley STAD, or if it's even something more advanced like Abacus or FEMAP or NX Nastran ANSYS. They all operate using a stiffness analysis approach. Let's talk a little bit about stiffness analysis so that you kind of understand how it works. I want to talk about a very, very basic problem. I got a bar and I'm yanking on it with some force F, and I want to know the deflection of that bar, an axially loaded bar. From mechanics, we know that the deflection is FL over EA. I mean, we've talked about that in here, right? That's pretty basic, okay? What I can do is I can rearrange this, and I can say that, you know, EA over L multiplied over here, and I get EA over L times the deformation equals F. Or what I'm going to call K times delta equals F. It's very, very akin to a spring problem that you did in physics, right? Remember those problems in physics where you have a spring and you're yanking it with some force F and you're trying to determine the displacement, and you say that F equals Kx, where K is the spring stiffness. Y'all remember that from physics, right? That's kind of what we're talking about here. We're trying to represent this in terms of forces, displacements, and the relationship between them called stiffness. That's why we're calling this a stiffness approach, right? And so it's akin to a spring stiffness problem from physics. Now that's a single bar. Now I want to talk about a truss. Now, when you see this problem, you're probably thinking method of joints, method of sections, you're thinking virtual work, all the stuff we've been talking about in here, but I want you to look at it a little bit differently. Isn't this just a bunch of bars? This is a single bar, this is a bunch of bars, right? Or more particularly, and I'm using this term specifically, an assemblage of bars, okay? What I want you to do is now think about how a computer would attack this problem. The way a computer is going to attack this problem is it's going to say, okay, let's, instead of looking at it like it's some big system, let's look at it like this. So what we'll do is we'll see, can we define a spring, if you will, for the whole structure? And so we put that in a matrix. We call that a stiffness matrix. Can we define a force for the whole structure, a force matrix or a force vector? And then use matrix algebra to solve for the unknown displacements. That is how a computer is going to handle this, okay? One of the benefits of applying a matrix approach is that computers love to do matrix algebra, all right? Computers are really only good at two things, counting and adding, okay? If you're playing, you know, Fortnite or League of Legends or whatever, that's all it's doing. It's just doing it really fast, you know, doing it a lot, okay? But that's all computers are doing. So what we can do is we can express the structure with this collection of spring constants and forces and solve for the displacements. And that's how a computer analyzes structures, whether they're determinate or indeterminate. And the best part is we can define a single method that works across the board. So this is how programs work, these structural analysis packages work. What you do as the user is you create the model, and that's kind of what we're going to work on today. It's what's called pre-processing. Pre-processing means creating the geometry, the joints, the members, the boundary conditions, the loads, the stiffness, you know, creating the model. And then you hit go. What the program does is it says, okay, I'm going to write a spring matrix, a stiffness matrix for the entire structure. It's going to write a force vector for the entire structure. It's going to solve this system for the displacements. It's going to take those displacements, it's going to sub them back into the members to get like the shears and moments, the internal axial forces, the reactions, etc. And it's going to spit you out the final answer. So you hit the little go button, it does all of this and gives you the answer. And then you as the analyst can go through and look at the support reactions, the shear and moment diagrams, etc. That's what's called post-processing. After the analysis is done, you query the results, okay? Does that make sense? That's kind of what MASTAN is doing. We're doing some really simple stuff in here, but if you're doing some really out there, funky FE modeling, you know, that's what this is doing. It's just this process exploded. You can use it For structural engineering applications, this is from some of the research I've been doing over the past couple of years. Geotech, you can use it for thermal stuff, fluids, you name it. It's all kind of the same process. Okay. All right, let's get started with MASTAN. What I want you all to do is go ahead and open MASTAN if you haven't already done so. I'm going to pass this out. This is our first sort of example tutorial. I'm going to walk through it with you. 1, 2, 3, 4, 5. I think that's enough. Wait, hold on. There we go. So the way this little tutorial is set up, it will literally step by step tell you everything that you need to do, but everything that's in this tutorial is also in the PowerPoint, so I can just hop back and forth between the PowerPoint and hop back and forth between the PowerPoint and MASTAN, which I'll do that. You are more than welcome to work at your own pace. However, it would probably be good if you tried to sort of keep up with what I'm doing, because I'm going to be explaining stuff as I go along. And it's the explaining stuff that's really going to help you on homeworks and your analysis project. So when you open MASTAN, it should look something like this. For those of you that were able to get the installation done, do you see this? Okay. All right. So let me explain in a nutshell how MASTAN works. You probably want to pay attention to this. So MASTAN works in a very straightforward fashion. Up here on the top are the menus. They contain all the commands necessary to define the model, run the analysis, query the results. Everything's up here. When you click a given command, what's going to happen is down here is going to pop up a data entry toolbar, and that data entry toolbar is going to be specific to the problem in question. Okay, so if you're trying to define nodes, it's going to have a node toolbar. If you're going to define materials, it's going to have a material toolbar. You enter in the data, hit apply, and that executes it. And you just go through these menus, and boom, you've got a model developed. Now, a couple things. So if you look up top, the first two menus are File and View. Okay, does everybody see that? So the File menu, obvious stuff, but there's a couple things in here that are pretty valuable. There's this thing called Print Photo. That's actually really cool when you're doing like homework assignments or projects, because you can have it export the view screen into a TIFF file, which is basically like a JPEG. So if you're like doing a homework assignment, you can export that into a photo instead of having to use the snipping tool. It's actually much more convenient. And you can create a report that generates a text file of all your displacements and deformations and all that stuff, and you can copy and paste that into Excel, etc. The View menu is where you zoom, rotate, pan. You can rotate in 3D fashions if you want. You can also use these define views to get back to like the front view, the X and Y, etc. You can also turn labels on and off, so that won't delete the data, but if you're like, I don't want to see the support conditions, you turn the label off for the Fixities and it'll go away. So now, this is important. There are generally two schools of thought when creating a structural analysis program. The first is to build a program that takes into account units for you and will convert them for you. It's convenient, but it does restrict the user on the unit system. The other school of thought is to don't incorporate a unit system at all. And some of the most, advanced structural analysis packages that you can buy, I mean, like Abacus. They use Abacus to design space shuttles. The most advanced stuff you can think of, and there are no unit systems incorporated in that at all. And the idea is it's up to you as the analyst to choose a consistent unit system. So that's what MASTAN does. Okay. So as the analyst, you need to adopt consistent units. And my suggestion to you is to use forces in kips, lengths, and inches. The reason is so that your displacements at the end come out in inches, and most of your loads are defined in kips anyways. So when you define distributed loads, they need to be in kips per inch. And whenever you look at like moment diagrams, they're going to be in inch kips. That doesn't matter today, but it'll matter on Wednesday. All right, some ground rules. So a couple things. First off, some terminology. When you think about trusses, you're probably thinking of like joints and members. I'm going to throw out some new terms, the term node and element, okay? So joint and node, I'm going to use interchangeably. Member and element, I'm going to use interchangeably. I got some more specific definitions for what those terms mean here in a bit. Units, again, convert everything to a consistent unit system before beginning, and we typically use kips and inches. On your homework 7, you're going to use kips and inches. All right, sign convention. We're writing a bunch of equations, in matrix fashion, and so in order to do that, we have to refer to our quantities consistently. So what we do here in most structural analysis routines is we say that for the x direction, forces and displacements to the right are positive. For the y direction, forces and displacements upward are positive. For rotations, or moments, we take counterclockwise as positive. Axial forces, we take tensile forces as positive. Everything else, shears and moments, tend to follow, bless you, what we normally do. We could expand this to 3D, but we're not going to do 3D in here. We usually stay in 2D in civil engineering anyways. All right, here's how you create a structural analysis model in MASTAN. So the first thing you do is you define the geometry. So that's the nodes and the elements, the connections, that's the internal hinges. You define the properties, so that's the material properties, the section properties, and then attach them to the structure. You then define the conditions of the model. Conditions are like the support conditions, we call those fixities in MASTAN, and then the loads, the forces, the moments, etc. We perform the analysis, and then we post-process the results. And see these red bolded words right here? I'm just getting that from right here. So you literally start here, work your way over, and you're done. Like it's really simple, okay? With me so far? Okay. So this is the problem that we're going to do. This is akin to a truss that we did earlier this semester, but I've changed it up a little bit. I wanted to use W sections because your project uses W sections, and I wanted to show you how you can utilize that in MASTAN. We're going to use E as 29,000 KSI for all members. So I would go ahead and open MASTAN, and the very first thing that I would do whenever you use MASTAN, File, Save As, and save your file somewhere of your choosing in your computer. Now, whenever you save it, this is a program that is MATLAB based, so your file name needs to follow MATLAB conventions, so no spaces in your file name. Alphanumeric letter terms only, so for your file name use letters, numbers, or underscores, nothing else. And it's got to start with a letter. So if you look on your handout, I said something like ex30.mat or something like that. That fits the name convention. Sound good? Okay. Now, as you're working on this, I want to show you something on the slideshow. Look at this. See this little thing right here, this little legend? So we're going to start working on this file, and then I'm going to skip ahead a little bit. Okay, see now over here, see in this section how I've gone to the next part. So as you're working on this on your own, you can kind of see where we're at. So I did that so that we could all sort of follow along. Okay, let's talk about geometry. That's the first step. That's defining the nodes and the elements. All right, let's talk about what nodes and elements are. So we are using a matrix stiffness analysis process that's really a specialized approach of what's called finite elements. Have any of you ever heard of finite element analysis? I think maybe some of you have. So the way finite element analysis works, I'm not turning this into a graduate course, but finite element analysis is basically a means of taking a bunch of differential equations and turning them into linear equations. That's kind of what finite element analysis is in a nutshell. So in that world, a node is where the software will directly compute the deformations, okay? So in matrix analysis, everywhere else the deformations are interpolated, okay? So whenever you're building a structure, this is where you should put nodes. You should put them at support locations, you should put them at internal hinge locations, at truss joints, at wherever you're putting a point load, and at any other point of interest on the structure. Like if you have a point you want to know the deflections there, you should have a node there. So if you look at figure 2 on your handout, which I'll show you here in a second, I have 5 nodes. Those are the nodes that we need for this problem. Elements are, well, in matrix analysis, the model is broken down into discrete solution regions called elements. And so in nonlinear analysis, that can matter. The way I sort of describe that is if you have a function, right, what we're doing is we're taking that function and we're splitting it up into sort of like, like this, sort of like these straight line segments, right? And so the idea is that the more elements that you use, the better your answer will be. Does that make sense? But if I have a model if this is the function I'm trying to interpret, it doesn't matter if I use one straight line segment or if I use like 100, right? I'm going to get the same answer. So we're doing linear problems in here. So one element per member in your structure is more than enough. If we're doing nonlinear problems, you might need more elements. But for us, that doesn't really matter. So another thing to think about in defining structural geometry is the coordinate system. See, whenever you're building a model, what you need to define is, let's say we have a beam here that's 100 inches long. You need to define a beam that's 100 inches long. You could say that this is 0, 0, and this is 100, 0. You could say that this is 25, 0, and 125, 0. You could say that this is 0, 36, and 100, 36. You could say this is negative 150, 25, and negative 50, 25. The only thing that matters is that you have defined a beam that's 100 inches long. All you need is a consistent origin. So here's the analytical model that we're going to use, and this is figure 2. So I'm placing my coordinate origin, or my origin of my coordinate system right here, and here are the nodes that I'm going to use, and here are the elements I'm going to use. Okay. We also need to adopt consistent units, but there actually is a benefit in the fact that this is MATLAB based, is that when we input the coordinates, we can say, like for N2, we could say 144, or we can literally just enter 12 times 12, and it will do it, okay? So we don't have to do the math ourselves. We can just input 12 times 12, and it will know where to place the node, okay? So here's how you define nodes. Let me escape out of this and go to MASTAN. And so you might have already passed this while you're working on this yourself, but I'll go ahead and do it with you. So I'll build a couple things with you, and we'll see how this goes. All right. So the first thing I'm going to do is File, Save As. We'll go to the desktop. We'll call this example, or X30. I'm going to skip the title definition. Actually, you know what? No, let me put that there. Define title. Let's do that. Let's not be lazy. So we're going to define a title. Let's do lecture 30 example problem. Hit apply. Hit cancel. And one of the things that you'll see in the handout is that I recommend that you save often. So I'm just going to hit file and save. If you look on top here on the toolbar, you'll see where it says 10:35. That's the time that you last saved it. So you as the analyst will know when you saved it last. So we'll go to geometry, define node, and you got to enter in numbers for all three. You got to do X, Y, and Z. So we'll do 0, 0, and 0, and hit apply. And then instead of 144, I'll just do 12 times 12 and hit apply. And it knows that that's 144. So if you notice on page 2, I gave you the node coordinates for this truss, so you don't have to figure that out. So this one's 24. This one's 6, and this is 8 times 12. Yeah. and this one is 18. All right. And what you should see now, after you get done, you hit cancel, you should see this. Does everybody see this? Is everybody able to do that? Does anybody have any questions on that?
How can you undo it if you made a typo?
That's a great question. So if you made a typo, okay, what you can do is you can go to Geometry, Remove Node, and you could say, click Node 5, like click Node 5 on the screen, and then just hit Apply, and now Node 5 is gone. And so now I need to define Node 5. So that's a great question. Okay, is everybody okay with that? All right. Has everybody been able to define the nodes? All right, tell me if not, because I'm going to move on.
I'm still working on it.
You good?
Yeah, I'm getting there.
Okay, all right. Now let's go to, let's discuss elements. One thing to note about elements is that it doesn't really matter in terms of the answer, but it is common practice, and I want you to get into this habit of defining elements from the lower number node to the higher number node, okay? The reason why is that, like for a truss, it won't matter, but like for a beam, your shear diagram will be flipped if you don't do that. You know, it's common practice to do from lower number node to higher number node. So now what I'm going to do is I'm going to go to MASTAN, and I'm going to go to Geometry, Define Elements, and I'm going to use my little either Figure 2 or Table 2. Like Table 2 says element 1 goes from N1 to N2, N2 to N3, N4 to N5 to sort of handle that. And what you do is you use your mouse clicker and you literally just click N1, click N2, hit Apply. Click N2, click N3, hit Apply. Then N1, N4. Notice how I'm going from lower number node to higher number node. N2, N4, hit Apply. N2, N5, hit Apply. N3, N5, hit Apply. So what your model should look like is this, okay? And the members should be like dashed or particularly dash dotted, like they should kind of look like fuzzy lines. Is everybody seeing that? How about y'all in the back? Are you good? Okay. Let me see. I want to see where everybody's at. Okay, you're ahead. This is great. You're ahead. This is great. This is great. Great. How are we doing?
Is there any way you can change these numbers?
What do you mean change them?
I put it in a different order than yours.
You can go to Geometry and like renumber nodes, but with elements you probably need to remove them and restart. But it doesn't really matter. I just want to like for a truss analysis it won't matter, but later on it will. You'll see what I mean. For now. All right, how's yours? Oh, that's right, that's right. Good, good. Oh, wow, you're way ahead. Okay. Okay, all right. So now what we're going to do is we're going to go to Properties. Now, it actually doesn't matter what order that you do the properties in. You could do Material, then Section, or Section, then Material. But I'm just doing it in the order that it's programmed in. What we're going to do is we're going to go to Properties, Define Section. Now for this truss, how many different W sections are we using for the problem as a whole? We're using two of them, right? We're using a W12 by 22 and a W12 by 16. Does everybody see that? You can look at table 2 and you'll see what I'm talking about. So I could go to the steel manual and I could enter in all that data right here, or I could check this database option. And when I check this database, this pulls up the AISC shape database, and I can go to W12 by 22, and watch what happens when I click 12 by 22. Not only has the section been named, but all the data for the 12 by 22 is pre-programmed in. So when you're doing your project, you don't need to do that. It's got the W12s built in. Sound good? So we hit apply, and that will create section 1, and then go to the 12 by 16, hit apply again. That will create section 2. I'm creating 2 sections because there's 2 elements. Now, the way of describing this property section is, imagine this, what I did just now is creating buckets of paint. I created a red bucket of paint with the W12 by 22, and I created a blue bucket of paint with the 12 by 16. But right now, the structure is not painted. So what I need to do is paint the structure with those properties in the appropriate locations. And so what I'm going to do is, if you go back to our model, we've defined the horizontal model, the horizontal elements with W12s by 22s, and the diagonals with W12 by 16s. So let me hit cancel, and what we'll do is we'll go to properties. Now we're going to attach a section. That's painting. So attach a section. We're going to click this, this, and this. So those horizontal elements, and I'm going to make sure that I pick the W12 by 22. I can move over to the W12 by 16 if I want, but I'm going to pick the W12 by 22, hit apply. Now when I hit apply, you'll see that the members now look a little different. Instead of this dash dot, dash dot, dash dot, now they're just dashes. What that means is that they have a section property applied, okay? So I'm going to hit, now what I'm going to do, and this is important, I put this on the instructions, you hit clear so that you deselect those members. Now I'm going to select the other ones. I'm going to hit the W12 by 16, so now I know I've got the diagonals. Then I'm going to attach the W12 by 16, hit apply. Now, if I hit clear, now all the members look different. They all have section properties attached, but they do not have a material attached. So what I got to do now is I got to go to properties, define a material. Now for this problem, all the elements are made out of steel. So what I'll do is I'll create a single material. I'm going to call the name steel. I'm going to change the E value to 29,000. Hit apply. So again, that created my bucket of paint, and now I need to make all the members steel. I need to paint the structure. So I hit properties, attach materials, and then instead of selecting each one of the elements one by one, I'm going to click the all button right there. I'm going to click that all button. Now that selects them all. Hit apply, and cancel to get out of that. Now look at the elements. Now see how they're all solid? This is a very good debugging feature. If your program isn't running, check to see if all the elements are solid. Because if they're not, that means you haven't defined some material properties. Okay? With me so far? All right, I want to stop for a sec. We still got time, and we're going to do this all in lecture tomorrow. But is everybody at this point? Is everybody here? Does anybody have any questions getting here? All right. Now what we're going to do is we're going to define our conditions. So in order to define a model, you need to define the geometry, You need to apply the properties to that geometry, and then you need to define conditions. Conditions are the support conditions, the loads, etc. Now for this problem, this was a hinge support. This was a roller support. So what we're going to do is we're going to say, okay, let's go to conditions, define fixities, and then I'm going to select node 1. Now node 1 is a pin support. Remember, pin supports carry reactions in the x direction and the y direction. So I'll check those two and hit apply. And if you look, you'll see here on the screen, now we got some red arrows right there. Those red arrows indicate that there's a pin support there. Now, what happens is if I just click node 3 and like hit apply again, it puts an X and Y reaction there as well. But that's incorrect. I only want a roller there. So what I need to do is I need to clear out my selection, click node 3, and make sure that only the Y displacement is checked, and hit apply. Okay, so you can reapply fixities till you're blue in the face, you know. So you should have an X and Y here and a Y there. And as for the loads, what we can do is N2 and N4 both have a downward load of 50. So we go to conditions, define forces. N2 and N4 both have a downward load of 50. So if you remember sign convention, consistent sign convention, downward loads are negative. Downward loads, negative 50 on the PY. And so you have downward green arrows. The green arrows are the loads, the red arrows are the support conditions. Now we need a horizontal load right here that's positive 35 because it's yanking 35 in the X direction. So clear, here, do 35, and then you hit apply, and you're like, wait a minute, why is there a horizontal and a vertical? Because you forgot to clear that out. MASTAN automatically retains your load definition. So just click node 5, change that to 0, hit apply, and it'll make that go away. And now we have the truss, we have the loads, we have the fixities, the materials, the geometry. We're ready to analyze. And so all you have to do is you go to you go to analysis. And what we're doing in this class is a first order elastic analysis. So we do first order elastic analysis. For the analysis type, where it says space frame, we're going to change that to a truss, particularly a planar truss, because we're in the XY plane. Hit apply. And what you should see here is applied load ratio equals 1, success analysis complete. The analysis is done. All right. Just to show you real quick a couple of the things that it can do, check this out. So we go to results. We go to node reactions. I can click node 1, and now I see here's the reaction in the X direction, here's the reaction in the Y direction. I can go to node 3, get that reaction. All right, 49.17. I can go to results node displacements. So like node 5, I have a displacement in the X direction of 0.0556, a displacement in the Y direction of negative 0.08901. I can do the same thing with internal forces, results, element forces. Element 3 is experiencing an axial load of negative 38.75. That's 38.75 kips in compression, right? Because it's negative. Here's where it gets cool. I can go to results, diagrams. Let's do deflected shape, and let's make sure we can see it. So let's do a magnification scale of like 40. So what it's going to do is it's going to take those displacements, it's going to amplify them by a factor of 40, and so that's what the truss looks like after it's deformed, right? And if you really want to get crazy, you can hit the little checkbox where it says Animate, hit apply, and it will animate what the structure looks like before and after deformation. Yes?
What exactly do you want on the turn-in for the project?
We'll get there. It's literally 10:50 right now, so we're running out of time. But for a couple things, let me answer that two ways. For the project, you're turning in your M file, just the file.
So just, do you want the deflected
No.
shape over it?
No, like literally just the MATLAB file for the project.
Oh, okay.
For the homework, it tells you specifically what I want.
Okay.
It's very explicit. You won't miss it. So now Wednesday, I know we went through the software pretty quickly on the recording, but that's the beauty of recordings. You can always pause and go back. What we're going to do Wednesday is we're going to do a beam problem, and the beam problem has fixed supports. It has internal hinges. It has moments. It has a lot of the stuff that we didn't do here. Between the two, you'll have more than enough know-how to handle the structural analysis we do in here. Any questions? All right. That's all I've got for today. If you still had problems installing, come see me, and we'll see if we can sort it out. But that's all I got. I will see you all on Wednesday, and we'll pick this up.